So again, the next set of second class of FETs are MOSFETs. MOSFETs are abbreviated as metal oxide semiconductor feed effect transistor. How they differ from JFET? So the first class of FET we have studied the JFET in that classification. The next set of class are nothing but MOSFETs. So here the MOSFETs they differ from JFET in only one parameter. So considering whether the gate is connected with the channel or not. In case of JFET, there will be an PN junction and the gate will be in a direct contact with the channel. But where in case of MOSFET, the gate here is not in a contact, it will not be in a contact with the channel. Instead, it will be insulated from the channel. So means between the gate and channel, there will be an insulating layer that is going to separate them. So that layer is formed by the silicon dioxide material, or I can say this is a silicon dioxide layer which separates the gate from the channel. That's why the input resistance of MOSFETs will be higher than that of JFET. So since the gate is insulated, that's why these can also be called as IGFETs. IGFETs in the sense insulated gate if it is. Like JFET, MOSFET also has three terminals, that is gate, drain as well as source, and these are also an voltage controlled device. So voltage controlled device in the sense, so the output current, that is the drain current, is controlled by the uh, gate bias, that is VGS. Okay, so these are the symbols of MOSFETs. Here you can see the MOSFET N-channel. There are four types again. So broadly they are classified into two types: enhancement types and depletion types. So in case of depletion types, again the channel could be made up of N type material, or it could be made up of P type of material. Or in case of enhancement MOSFETs, so again the channel could be made up of N type material, or the channel could be made up of P type material. Based on that one, they are classified into N channel and P channel MOSFETs. So here the current direction is almost same. So actually in case of MOSFETs, there will be four terminals. So like gate, drain, source, and one more terminal will be there, that is substrate. So internally substrate will be always connected with the source only. So that's why three terminals are only brought out. So that brought out, and here you can see the difference in the enhancement and depletion type of MOSFETs. The current direction, the arrowheads are same only, but the only difference is, so this is the channel, there will be a channel, continuous channel here, and there the channel is not in a continuous manner. So channel won't be there during the construction in case of enhancement type of MOSFET, but in case of depletion type of MOSFET, channel would be there during the construction itself. So here channel won't be there during the construction, but channel will be formed during the operation. So these are the MOSFET symbols. Next we shall see the construction of n-channel depletion type of MOSFET. Here as earlier I told you, there will be four terminals. Actually there will be four terminals: gate, drain, source as well as substrate. But the substrate terminal will be internally connected with the source only. Here we shall see the construction. Very first, a lightly doped P type of substrate is taken here. From this lightly doped P type of substrate, two heavily doped, you can see here, two heavily doped N type materials are diffused. So that's why the heavy doping is indicated by the N plus symbol here. So N plus in the sense these two are heavily doped. So these two heavily doped N-type layers are diffused on the P-type substrate, and two metallic contacts are made. One is brought out as source, indicated by S. Another is brought out as drain, which is indicated by the D. So here on this entire setup, an SiO2 layer is grown on it, or SiO2 layer is deposited on it. On this SiO2 layer, one more metallic plate is deposited and an electrode is connected, which is brought out as gate terminal. So now the source, gate and drain terminals are there. Here you can see the gate, source and gate, drain and source, and internally the source and drain the source and drain are connected with the channel. So here, as earlier I told you, in case of depletion type of MOSFET, channel would be there during the construction itself. These two uh, these two terminals are linked with the channel here. So this channel is diffused, that is the diffused channel will be of n type material, it will be of n type material, that's why it is called as n channel depletion type of MOSFET. Okay, and here also you can see that the gate terminal is not in a direct contact with the channel here. Instead, this gate and the channel are separated by a insulating layer here, that is formed by the SiO2. That's why it is referred as IGFET, or you can say MOSFET. Okay, and in case of P channel depletion type of MOSFET, the difference you can see here. In case of N channel, P type of substrate was taken, and in case of P channel, N type of substrate. Sorry, 1 second. So here I have explained directly the working itself. Let's go to the previous slide. So here, in case of P channel depletion type of MOSFET, the only difference that would be there is the substrate would be of N type material. Substrate ಏನಿರುತ್ತಾ N type material ಇರುತ್ತಾ, and the two heavily doped materials are diffused. Heavily doped P type of materials means these are indicated by P plus ಅಂತ indicate ಮಾಡ್ತಾರೆ, and these two terminals are linked with the channel, and the channel would be again of the type of P type material. Again the entire construction will be same only, and since the channel will be of type of P type material, such kind of depletion type of MOSFETs are referred as P channel depletion type of MOSFET. Next, in the next slide we will see the uh, working of the N channel depletion type of MOSFET. So when we study the working of N channel MOSFET, this working could be studied in three different cases. First, we shall see the connection here. So as we know that this is a P type substrate, and the metallic contacts are here, and the gate is insulated from the channel over here, and the channel is of type of N type material. Okay, since the gate, we will apply the potentials like this between the drain and source, or you can say the drain is made more positive with respect to source. This is the drain terminal, and this is made positive with respect to source, means this would be negative and this terminal would be positive. And between the gate and source, we will apply a negative voltage, or you can say negative voltage, in the sense gate is made negative with respect to source. Gate is made negative with respect to source. So let us consider the first case. Whenever VGS is equal to 0 and VDS is applied, what happens whenever VGS is equal to 0? Let's say VGS is equal to 0 in the sense there is no potential applied, or you can say these two are shorted with each other. So whenever these two are shorted, what happens? On the application of drain to source voltage, keeping the gate to source voltage 0, or you can say VGS 0, the free electrons from N channel are attracted towards the positive potential of the drain terminal. The free electrons from the source are attracted towards the drain, means the electrons will flow from source to drain. As this drain terminal is more positive, the electrons, they get the repulsion force from the source terminal, but at the same time they get an attraction force from the drain terminal. So the electron will move from source to drain. This establishes a current ID. This establishes a current through the channel, which is to be noted, or which is to be denoted as IDSS. ID will be equal to IDSS. Maximum current will flow whenever VGS is equal to 0. That is the first case. Let me erase this. In the next case, VGS is made negative and VDS is applied. Means here the VDS is kept constant and VGS is made negative with respect to the source, or you can say the gate is made with negative with respect to source. So if you apply a negative gate voltage, on the gate, the gate will, since the gate is an uh, gate is at the negative potential, the gate will repel the this this will repel the conduction electrons from the channel, because the electrons are negatively charged and the gate is also negatively charged. In the sense, there will be a repulsion from force from the gate terminal, and these electrons will get a repulsion force from the gate, and it tries to move these out, move these conduction electrons out from the channel. At the same time, since the gate is negative, it tries to attract the holes from the p type of substrate. So I will tell you again, the negative gate voltage, it repels the conduction electrons from the channel because they are of the same polarity. So here the electrons are repelled, from the gate here, from the channel, and at the same time the gate is going to attract the holes from the p-type substrate. So these holes and the attracted holes and the repelled electrons, they combine with each other, or they recombine with each other. So there is a recombination happens here from the between the repelled electrons as well as the attracted holes from the substrate. And the level of recombination of electrons and holes, it depends upon the magnitude of VGS. Means ನೀವು ಎಷ್ಟು ಇಲ್ಲಿ ವೋಲ್ಟೇಜ್ ಕೊಡ್ತೀರೋ ಅದರ ಮೇಲೆ ಇದು ಡಿಪೆಂಡ್ ಆಗುತ್ತಾ. Due to this recombination, this channel is depleted of some of its electrons. So because earlier there were some electrons were present at the channel, but now due to the negative voltage of the gate, these electrons, they will get a repulsion force from the gate, means they move out from the channel. So the channel now it is depleted of free charge carriers, or you can say the channel conductivity now it is decreased. So channel conductivity is now decreased at some voltage. So at some point of VGS voltage, the channel is completely depleted of free charge carriers, or you can say that the channel becomes completely empty. Whenever the channel becomes completely empty, means there is no charge carrier that is flowing from source to drain. And if you measure ID current here, ID current, so that ID current through a millimeter, that ID current turns out to be 0. The voltage VGS at which the current becomes 0 is known as cutoff voltage, which is indicated by VGS off. VGS off. I mean to say, whenever VGS value is increased in the negative direction and if it becomes equal to the VGS off, the drain current will become 0 because of the decrease in the channel conductivity. And since the channel conductivity is now decreased, or you can say channel is depleted of free charge carriers, this reason or this mode of operation is known as depletion mode. This mode is referred as depletion mode. Now let us consider the third case, that is VGS is made positive with respect to means the gate is made positive with respect to source and VDS is applied. Okay. So now let's reverse these potentials. Means so the battery is reversed here like this. The gate is made more positive with respect to source. Source will be negative and gate will be positive. What happens? Since now the gate is positive here, gate is positive. So gate is made positive with respect to source. For the positive values of VGS voltage, the positive gate will draw additional electrons from the p type of substrate. So as we know that the p type of substrate, in the sense it won't be having only the holes, it will be having still minor number of electrons, and those electrons are attracted towards the gate terminal, in the sense they are attracted towards the channel. So since the more electrons are attracted from the substrate into the channel conductivity now it is enhanced, or again the channel conductivity is increased. And if the channel conductivity is increased now ID current will again increase, and now ID current will increase beyond the value of IDSS. So IDSS, what is IDSS? IDSS value was the maximum drain current whenever the VGS value is 0. But since we apply a VGS positive value, the ID current now it will increase beyond the IDSS value, or you can say the channel conductivity is enhanced, and this mode of operation is known as enhanced mode. Enhanced mode. Now we shall see the drain characteristics of n-channel depletion type of MOSFET. So for the drain characteristics, we have to draw the curve between the ID value and the VDS value for different VGS values. So as we seen in the previous session here, so previous slide, so the depletion type of MOSFETs can act upon two modes. So whenever VGS value is negative, it can be operated in the depletion mode, and whenever it is VGS value is positive, so the ID current increases beyond the saturation value, that is IDSS value, and the mode of operation is known as enhanced mode. So here you can clearly see from the characteristics curve. So whenever this is VGS value is equal to 0. So whenever VGS value is equal to 0, we get a maximum current value or saturation current value for the first case, that is IDSS. So this is for the first case whenever VGS is equal to 0 and VDS value is applied. For the second case, VGS is made negative. So VGS is made negative and VDS is applied. Means whenever VGS is made negative, the channel conductivity was decreased, or you can say the channel was depleted of free charge carriers. That's why we can see a decrease in the ID current. A decrease in the ID current. You can see here whenever VGS value is equal to 0, ID value is somewhat like this. Whenever VGS value is minus 2, it is like this. Whenever VGS value is minus 3, or you can say whenever VGS value is equal to VGS off, the channel conductivity becomes completely 0, or you can say the channel is completely depleted of free charge carriers, and the ID current is assumed to be 0, and this is known as cutoff region, or you can say cutoff region. Okay, and for the third case, whenever VGS value is made positive, it should be operated in the enhancement mode. Means the current is supposed to increase beyond the IDSS value or saturation value. You can see here whenever VGS value is made positive. So whenever VGS value is made positive, the corresponding current is more than IDSS. Whenever VGS value is plus 1, so it is more than IDSS. Similarly, whenever VGS value is plus 1.5, like this, if you go on increasing the VGS value, you will get more and more ID values, and this mode is known as enhancement mode. And the uh, characteristics curve below the 0 volt, or you can say VGS values 0 volt, this mode of operation is known as the depletion mode of operation. This is about the drain characteristics. Similarly, if you see the transfer characteristics, you can clearly see here from the picture. So transfer characteristics will tell the relationship between ID and VGS value, So as we see here, we can apply the positive VGS value also, as well as we can apply the negative VGS value also. Negative VGS value also positive VGS value. So whenever VGS value is equal to 0, the current is maximum, and that can be referred as saturation. Current achieves the saturation value, that is IDSS. Whenever negative VGS value is applied, the channel conductivity it will go on decreasing, or you can say the channel will go on depleting the free charge carriers from its channel. So means the current will try to decrease at some point of time. Whenever VGS value is equal to VGS off, the channel will get completely depleted from the free charge carriers, or the channel conductivity becomes 0 and ID current will be 0 here. Let's say whenever plus VGS value is applied, means if the gate is made positive with respect to source, now the current ID value, the channel conductivity, now it starts increasing, and you can get the current value more than IDSS. You will get a curve like this. The left region or the left mode of operation is known as depletion mode, where the ID value is less than IDSS, and in case of enhancement mode, this is the right region, so where the ID value is greater than IDSS. Okay. Now the same characteristics, the drain and the transfer characteristics of p channel anta nodtadra. So here the only difference is, so you can see here the drain characteristics. So here uh, for to operate the MOSFET in enhancement mode, the gate was made positive with respect to source, means VGS is positive, or to operate it in depletion mode, the VGS is negative voltage, but it is reverse here. To operate the uh, MOSFET, P channel MOSFET, so here you can see, so the reason above 0 volt means, the reason above 0 volt means -1, -2, -3, -4. These are nothing but these are enhanced mode ಅಂತ ಹೇಳ್ಬೋದು. And the reason below 0 volt, that is plus VGS values. These reasons are known as depletion mode. Similarly here also you can see here, for positive VGS value, are nothing but, so these are depletion mode, and for negative VGS value, this is going to do an enhancement of channel, or the channel conductivity is increased here, and the ID current value becomes more than IDSS here. This is an exact replica, or sorry, exact mirror image of the previous n channel depletion type of MOSFET. So otherwise the explanation it holds would same for both. The next is enhancement type of MOSFET. So as I told the difference between the depletion type of enhancement and the enhancement type of MOSFET, there would be only one difference. There won't be any channel. So as we seen in the previous case, in case of depletion type of MOSFET, the entire construction was same. Only the difference was there was a channel. So which could be of n type or p type, but here there is no channel during the construction. Since there is no channel during the construction, so this would be of type of enhancement type of MOSFET. And another difference is the depletion type of MOSFET was capable to be operated both in depletion mode as well as in enhancement mode, but this enhancement type of MOSFET is capable of operating, or it is capable of getting operated only in the enhancement mode, not in the depletion mode. Otherwise the construction details it remains same. Let's see the working of n channel MOSFET here. So for the working could be understood with two cases. For the first case, again you can see here the biasing method. If you see the biasing method, here the source is made negative with respect to drain, or you can say the VDS, the drain is made positive with respect to source here, and the gate is made negative with respect to, positive with respect to source here. Since it is capable of getting operated only in the enhancement mode, the gate should be made positive with respect to source. Let's say if there is a reversal of polarity here, you won't get any current here. That's why, or this cannot be operated in a depletion mode. That's why we make always the gate positive with respect to source. Let's consider the first case. Where VGS is 0. VGS is 0 means these two are shorted, so there won't be any potential, or these two are shorted anta helbodu, and VDS is applied. What happens? On application of drain to source voltage, VDS applies voltage, keeping gate to source voltage 0, or you can say by directly connecting gate terminal to the source. So practically initially there won't be any channel. So consider this case, there won't be any channel initially. So that's why even though this terminal is made positive with respect to source, drain is made positive with respect to source, there can be a repulsion force from the source terminal, and there can be an attraction force from the drain terminal. But since there was an absence of channel, the charge carriers they cannot move from source to drain, and practically zero current will flow, or you can say E MOSFET is said to be in off condition. Yavaga whenever VGS is 0 volt, and VDS applied, and practically ಏನಾಗತ್ತ, So practically here 0 current will flow, or you can say ID will be equal to 0 volt. In second case, in second case, so whenever VGS is applied, or you can say VGS is made positive, VGS is made positive, and as in the previous case, VDS is applied. What happens? Let's consider. Let's erase this. Uh, Now gate is made positive with respect to source. What happens? Let's say gate is made positive with respect to source. Gate is positive. So since the gate is made positive, since we have p type of subset here, in case of p type of subset, no doubt the holes are majority in number, but still they will be having some electrons also. These electrons, they get an attraction from force from the gate now. Now, so as we make the as we vary the gate to source voltage, or as we increase the level of gate to source voltage, if the gate is made more and more positive with respect to source, it will attract more and more electrons towards the gate terminal. So since the more and more electrons are attracted towards the gate terminal, at some point of VGS voltage, uh, a channel is formed, and the electrons now that are repelled from the source, they will move towards the drain terminal, or you can say at some point of VGS voltage, a significant amount of current ID is observed. The voltage at which the channel is formed and the significant amount of ID current is observed is known as threshold voltage. I repeat, the voltage VGS at which a channel is formed and a significant amount of current is drain current is observed is known as threshold voltage. So if you increase the value of VGS voltage beyond the threshold voltage, so you will see a significant amount of increase in the drain current, because since the channel once the channel is formed, more and more electrons from the source now they are uh, attracted towards the drain ಅಂದಾಗ, so ಅವಾಗ ಏನಾಗುತ್ತಾ, so more and more drain current ಬರಲಿಕ್ಕೆ ಸ್ಟಾರ್ಟ್ ಆಗುತ್ತಾ. Okay, we can summarize as, for the positive gate to source voltage, for the positive gate to source voltage, it has enhanced the channel conductivity, or you can say uh, the enhancement type of MOSFET was operated in the enhancement mode ಅಂತ ಹೇಳ್ಬೋದು. Okay, and there is no depletion mode here. Now we shall see the characteristics, drain characteristics as well as the transfer characteristics of n channel enhancement type of MOSFETs. So here the drain characteristics are nothing but these are the curves between the drain current ID and the drain to source voltage, that is VDS, at constant gate to source voltage, or keeping the VGS value to some constant value. So here, looking at the figure, we can say that as the VGS is increase beyond the threshold voltage, so if the VGS is increased beyond the threshold level, the density of free carriers in the induced channel increases, and that increases the drain current. You can see here, let's consider threshold voltage is 3 volt. Up to the value of 3 volt, up to the VGS value up to the value of 3 volt, there was no channel induced, or you can say ID value is almost 0. Here the ID value is 0 here. Whenever the VGS value is increased in the positive direction beyond the VTH, so in this figure we assume that the VTH value is how much? 3 volt. So until the VGS value is less than 3 volt, there is no channel induced between the drain and source, and practically ID current is assumed to be 0. Whenever VGS value increases beyond VTH value, you can see here 3, 4, 5, 6, 7, 8. So if VGS value is increased beyond VTH value, you can get a significant increase in the amount of ID value here. You can see here for 7 volt it is approximately around 7 milliamps. For 8 volt it is approximately 10 milliamps here. So if you go on increasing the VGS value in positive direction, you will get more and more ID current. So this is about the drain characteristics. And regarding the transfer characteristics, you can see here you have done the practicals also. You have done this experiment in the practicals also. So here it is clearly seen that until transfer characteristics are nothing but these are the curves between the ID and VGS, keeping the VDS value constant. You can see here until the VGS value is 3 volt, or you can say the threshold volt, as we have seen in the previous case, VTH was assumed to be 3 volt. Until the VGS value is 3 volt, the ID current is almost 0. After 3 volt, the current it starts rising. Current ಏನಾಗುತ್ತೆ rise ಆಗ್ಲಿಕ್ಕೆ start ಆಗುತ್ತೆ. Simply you can say ID will be equal to 0 whenever VGS value is less than or equal to VT, that is threshold voltage, and ID increases if VGS value is greater than VTH. Okay, this is about a N channel. And for the P channel we will show this for the P channel operation. Again the operation and the working principle will be entirely same. The only difference is, so here the VGS, in the previous case the threshold voltage as well as the VGS values are assumed to be positive, and here they should be assumed to be negative. So as the VGS value is more and more negative, so the ID current increases. So this is the enhancement mode of operation anta helbodu. And this is the transfer characteristics. So ID versus VGS. So transfer characteristics kuda nodbekadra VGS should be taken negative. So that's why second quadrant ತೆಗಿಬೇಕಾಗುತ್ತಾ. So you can see the curve here. You can see the curve, the exact mirror image of this curve. This is an exact mirror image of the previous curve. So previous curve is the exact mirror image. Otherwise all the operation will be same. The charge carriers will be holes here. So next one is the that is complementary metal oxide semiconductor. CMOS is nothing but it consists of both P channel PMOS MOSFET or P channel MOSFET as well as N channel MOSFET on the same substrate. ಅಂದ್ರೆ ಒಂದೇ ಸಬ್ಸೆಟ್ ಮೇಲೆ ಪಿ ಚಾನಲ್ ಮಾಸ್ಫೆಟ್ ಮತ್ತು ಎನ್ ಚಾನಲ್ ಮಾಸ್ಫೆಟ್ ನ ಎರಡನ್ನೂ ಕೂಡ ಫ್ಯಾಬ್ರಿಕೇಟ್ ಮಾಡಿರ್ತಾರೆ. ಸೊ ಅಂತ ಒಂದು ಮಾಸ್ಫೆಟ್ ಗೆ ನಾ ಏನಂತ ಕರಿಬೇಕಾಗತ್ತಾ, ಕಾಂಪ್ಲಿಮೆಂಟರಿ ಮೆಟಲ್ ಆಕ್ಸೈಡ್ ಸೆಮಿಕಂಡಕ್ಟರ್ ಅಂತ ಕರಿಬೇಕಾಗತ್ತಾ. ಸೊ ಕಾಂಪ್ಲಿಮೆಂಟರಿ, ವೈ ವಾಟ್ ಡಸ್ ದ ಮೀನಿಂಗ್ ಆಫ್ ಕಾಂಪ್ಲಿಮೆಂಟರಿ ಮೀನಿಂಗ್ ಹಿಯರ್, ವಾಟ್ ಇಸ್ ದ ಮೀನಿಂಗ್ ಆಫ್ ಕಾಂಪ್ಲಿಮೆಂಟರಿ ಹಿಯರ್ ಅಂತ ನಾವು ನೋಡೋದಾದ್ರೆ, the P channel MOSFET operation is entirely a complementary to the N channel MOSFET operation. They are exactly reverse of each other. So that's why the name complementary. CMOS, why the CMOS is preferred ಅಂತ ನೋಡೋದಾದ್ರೆ, the basic advantage of CMOS over the previous FET's versions are, the very first advantage is this is going to consume very low power. This is a very low power consuming device, as well as you can achieve the fast switching operation, or you can say high speed operation kuda idralli irutta. For these two reasons, so the CMOS is preferred than the previous versions of FET. For NMOS transistor, for you can see here there are two transistors, they are symbolically shown here. This is an NMOS transistor, I can write it here, NMOS. For NMOS transistor, if the input, if the gate is made 1, then switch will be on, means the charge carriers can able to flow from source to drain. If the gate is 0, so that means there won't be any bridge from source to drain, means there won't be any charge carrier flow, or you can say the current will be 0, or you can say this is switch is in off condition. Similarly, in PMOS transistor, if gate is made 0, then I can say the switch is in on condition, or I can say the charge carriers are allowed to flow from source to drain. And if it is 1, then the channel or you can say the bridge is assumed to be broken between the source and drain, and there is no charge carrier flow from source to drain, and uh, this switch is assumed to be in off condition. This switch is assumed to be in off condition. Let us discuss the one important feature of the CMOS. This question would be asked for 5 marks in your examination. So as we seen in the previous case itself, why these are preferred over the previous versions anta nododadra. First one is the low power consumption property, another one is the high speed operation property. So can you tell how you tell that it is going to consume the low power than the previous versions of FET? The power consumptions are basically classified into two types: static power consumption as well as dynamic power consumptions. These two power consumptions are said with respect to the popular CMOS device that we are going to use in our electronics is inverter. So let us discuss these two features considering the inverter here. So as we see inverter here, first for the case of static power consumption. So static andre idra artha enappa andra constant. Remember, so these two switches are assumed to be in, they are to be assumed to be in connected in series. Let's say this is one switch, this is another switch. At any point of time, if you see the value of output, it will be either 1 or it will be either 0. Means that since these two switches are complementary to each other, if one switch is in on condition, another switch should be in off condition. Okay, let's say this is in on condition and this is in off condition. Let's say the first switch was closed and second switch is open. Let's say this is closed here, close agite anta tilkollona, and this is open. What is the, if you measure the effective current here at the output, so here to connect madida takshana, if you measure current output here, current, if you see the current is predicted by the switch or the transistor which is in the off condition, or which is, you can say, which is in the which is not getting on, or which is not operated. So ಯಾವ್ದು ಆಪರೇಟ್ ಆಗ್ತಿಲ್ಲ, ಯಾವ್ದು ಝೀರೋ ಐತೆ ಅದನ್ನ ನೋಡ್ಕೊಂಡು ಪ್ರಿಡಿಕ್ಟ್ ಮಾಡಬೇಕಾಗುತ್ತಾ. ಸೊ ಎವರೇಜ್ ಅಂತ ನೋಡೋದಾದ್ರೆ ಲೆಟ್ಸ್ ಸೇ 5 ampere is flowing here, 5 ampere flow ಆಗತ್ತೆ ಅಂತ ತಿಳ್ಕೊಳ್ಳೋಣ. 5 ampere can flow through the on switch, but the same 5 ampere is broken down here. This is not a continuous path, so 5 ampere may come till here, but if you measure the current at this point, so if you measure the current at this point, it will be again 0 only. Or if you assume the reverse case in the sense, let's say the first switch is in switch is in off condition and second switch is in on condition. Let's say again 5 ampere current is flowing through here, flowing through the first switch. So as the this circuit is not continuous, it is broken down here. 5 ampere may come till here, but from here onwards 0 ampere current will flow, and if you measure the current output here, again it will be predicted as 0. So that's why during the static condition, means whenever the output is 0 or whenever the output is 1, one of these switches will be in on condition, another switch will be in off condition. Since they are connected in series, the DC current is determined by non-conducting device. So in first case ನಾವು ನೋಡಬಹುದು, here it is the non-conducting device, ಇದನ್ನ ನೋಡ್ಕೊಂಡ ನಾವು ಇಲ್ಲಿ 0 ಅಂತ ಹೇಳಿದ್ವಿ, and here now it is non-conducting device, ಇದನ್ನ ನೋಡ್ಕೊಂಡ ಇಲ್ಲಿ output ಏನು ಹೇಳಿದ್ವಿ 0 ಅಂತ ಹೇಳಿದ್ವಿ. Since the current through the non-conducting device is 0, the power dissipation is assumed to be 0 in case of static condition. Similarly, in case of dynamic power consumption discussion ಮಾಡಬಹುದು. Dynamic ಅಂದ್ರೆ ಏನು? Changing. So let's say whenever the value is getting switched from 1 to 0 or 0 to 1. So let's say output is changing from 1 to 0 or 0 to 1, or if you represent this with a waveform, so these are the levels, or you can say these are the static conditions, and this is the point of time, so where the value is getting changed from 0 to 1, or this is the point of time where the value is getting changed from 1 to 0 at this point of time. So I am telling you exactly at the edge, at this point of time both switches will be in on condition. ಎರಡು switches ಏನಿರ್ತಾವ on condition ದಾಗ ಇರ್ತಾವ. Since the both switches are in on condition, but since on condition ಅಂದಾಗ obviously ಏನಾಗಬೇಕು, so ಇದು ಕೂಡ let's say first switch ಕೂಡ ಏನೈತೆ off on ಐತೆ, second switch ಕೂಡ ಏನೈತೆ on ಐತೆ. Let's say this is second switch, and let's say the first switch and the second switch both are in on condition, means current will flow in both the cases. Since they are connected in series, current through them will be same, ಎರಡು ಕೂಡನು current flow ಆಗುತ್ತೆ. But the thing is, now you can say that, so since the current is flowing through both of them ಅಂದಾಗ power consumption should be high, V into I should be high. But the thing is, this current is made to flow through these switches only for the short duration of time. Short duration ಅಂದ್ರೆ very small, ಅಂದ್ರೆ ಇದರ ಅರ್ಥ ಏನು, let's say for the amount of nanosecond or for the amount of microsecond, for very small amount of time or for small very small interval of time, the current is allowed to flow, maximum current will flow here. But since the current will flow only for the short duration of time, again the average power, if you consider the average power of consumption, so again the dynamic power also consumption will also result in a value 0. So since the static power consumption also is 0 watt and the dynamic power consumption also will be 0 watt, I can say the CMOS is going to consume low power, or it is a low power consumption device ಅಂತ ಹೇಳ್ಬೋದು. Okay, now we shall see the popular application of the CMOS inverter, which is nothing but an inverter. So this question will be asked for 5 marks. Let's see whether it works as an inverter or not. As you are sure with the NOT gate here, in the digital electronics you have seen the NOT gate operation. If the input is 0, the output will turn out to be 1, or if the input is 1, output will turn out to be 0. Let's see whether it happens here or not. Let's say if the input is 1, remember, so 1 will come at the NMOS here. So let's say this is NMOS and this is P MOSFET. So since these two are connected in series, so regarding construction ಹೇಳಬೇಕಾದ್ರೆ ನೀವು ಇಲ್ಲಿ ಹೇಳ್ಬೋದು, so the source terminal of the PMOS transistor is connected to a VDD source, and similarly the source terminal of this is the source terminal of NMOS transistor is connected to ground, whereas the drain terminals of both NMOS and PMOS are shorted together. ಇವೆರಡು drain terminals short ಮಾಡಿ output is taken from here, and the gates of these two transistors, NMOS as well as PMOS transistors, are shorted together, where we apply actually the input. Okay, if the input provided is 1 anta kotra, okay, no doubt 1 will go here at the NMOS, and with 1 will go at the PMOS as well. As we seen in the slide here, if the input is 1, NMOS will be in on condition, otherwise it will be off. And for PMOS, if input is 0, the switch will be in on condition, otherwise it is off. Let's see here. So since for PMOS input is 1, obviously it will be in off condition. And similarly for the NMOS, since the input is 1, it will be in on condition. So ಇದರ ಅರ್ಥ ಏನು, as if first switch is off and second switch is on, and since you are measuring current here, so voltage here, this is output. You can say this output is, since this is an on condition, whatever may the previous voltage value, so that output will be drained towards the ground, means output will become 0. For input 1, the output turns out to be 0. Let us consider the second case. Whenever input is 0, the NMOS will get, PMOS will get turned on and NMOS will get turned off. So whenever NMOS get turns on, so this become a complete circuit. So voltage that appears at the source terminal here, same voltage will appear at the drain terminal as well. So since from the drain terminal you are getting an output here, so output will be equal to 1. So if this was in on condition, this output will be drained towards the 0. But since this is in off condition, you can represent with a switch diagram like this. Let's say this is VDD, or you can say 5 volt. So since we are measuring the output here, so obviously it will be 5 volt only, 5 volt only. So you will be getting a output 1 here. So like this, for the first case, if you have provided a value 1, the output turns out to be 0. For the second case, if the input is 0, output will become 1. That's why we can say the CMOS can be used as an inverter. Thank you.